Welcome to the Judgment Call podcast, a podcast where I bring together some of the most curious minds on the planet. Risk takers, adventurers, travelers, investors, entrepreneurs, and simply mind-bogglers. To find all episodes of this show, simply go to Spotify, iTunes, or YouTube, or go to our website, judgmentcallpodcast.com. If you like this show, please consider leaving a review on iTunes or subscribe to us on YouTube. This episode of the Judgment Call podcast is sponsored by Mighty Travels Premium. Full disclosure, this is my business. What we do at Mighty Travels Premium is to find the airfare deals that you really want. Thousands of subscribers have saved up to 95% in their airfare. Those include $150 round-trip tickets to Hawaii from many cities in the US, or $600 life-flight tickets in business class from the US to Asia, or $100 business class life-flight tickets from Africa round-trip all the way to Asia. In case you didn't know, about half the world is open for business again and accepts travelers. Most of those countries are in South America, Africa, and Eastern Europe. To try out Mighty Travels Premium, go to mightytravels.com/MTP, or if that's too many letters for you, simply go to MTP, the number 4, and the letter U.com to sign up for your 30-day free trial. Mark, thanks a lot for coming on the podcast. Really appreciate that. Thanks for taking the time. So when I go to your website, I found this incredibly interesting. You actually have 4 different introductions of yourself. So one is short, one is long, one is pompous, as you call it, and one is more historical. Which one do you like the most?
I like the shorter the better. I'm not one for talking about myself too much, but there's some context in the longer ones which is sometimes helpful, because I'm, it's hard to put me in a box in a particular category of things, because I've wandered all over the place in my studies and in my work, and so people come from knowing me from different angles, and so I try to present a little bit of that history.
Yeah, I think it's incredible how you say this, how understated you are and how humble you are. A lot of your co-workers and people that know about physics describe you as the Richard Feynman of our generation, which sounds like an incredible honor already.
That's far too much of an honor, but I'm humbly thankful. and if I would hope that has something to do with the fact that I try to communicate and share what I learn in popular writings as well as in more technical work, because I think it's important to share the insights that we have at a more popular level. Not everybody thanks you for that, but I think it's the responsibility of science to communicate to a wider audience.
A lot of people coming from a computer IT background, they know you're from one of the creators, or the creator, correct me, what's the correct term there, of CF Engine, which is described as a way to control your computer's immune system, correct?
That's true. It's it was when I was a postdoc at the university here in Oslo many years ago, 30 years ago. As many people do in the natural sciences, I got involved in managing the computers, the networks, and all of the networking was coming up at the time, the Unix-based systems. And, I'm a person who likes to get my hands into the system and really understand everything. I need to take everything apart and put it back together and make sure I understand how it works. And I did that for a few months, and then after a few months, it started to be less interesting, shall we say, to spend as much time as needed to be spent maintaining systems, because not everybody realizes it, but the computers don't simply manage themselves. They need continuous assistance, maintenance, cleaning up, garbage collection, updates, upgrades, all of this kind of stuff. And so to cut a long story short, I decided it would be much more fun to try to automate that, to write a computer program, a smart computer program, if you like, a kind of artificial life kind of program to to allow the computer to become a kind of a living thing, like a biological entity, and manage itself as organisms do, to make sure its vital functions are going well. The heart rate is good. It's not overstressed. All the garbage is being collected. All the blood is being filtered, etc. And any harmful programs or viruses or whatever might come into, or even users for that matter, because humans are often the big problem. All of those things are being dealt with in real time, because life, of course, is a real time process. It's not set you on your career path and boot you out the door and everything's fine. It's a continuous process of learning, adapting, cleansing, maintaining the system. So CF Engine was a program that I developed over many years. I wrote the initial version in just a few months to really try to turn every individual computer into its own self-sustaining organism, entity that would look after itself, so that I didn't have to do that. And then over time, I realized that there was a total lack of this kind of software in the industry, and I shared it as open source. CERN took it up first, the particle accelerator labs took it up first, and then gradually it spread around the world and became very popular. And then many years later, I even started a company around this, but that's the long and the short of it.
Yeah, I think this is a complexity that few in the industry want to really look into, right? It's kind of a liability thing, and there's just this automation complexity that a lot of people underestimate. There's so many different parameters and things that can go wrong on this level, right? So it's usually left to human intelligence, to the system administrator, as you say, to do all these tasks. Because I know this from my own experience, if you, say, have the wrong version of the wrong library installed, the whole system stops working. And it's incredibly frustrating. So nobody wants to really be responsible for this, and it's being pushed around in IT circles. The package management pushes it to a lower category, says, oh, well, you have to manually upgrade. And then you're like, well, it takes hours. And you're like, well, shouldn't that be something that package management should do, for instance? And that's really disappointing. So a lot of people try not to go into these levels of complexities. How big is that project now? How many people use it? How many downloads were there on GitHub? Do you have any of those statistics?
I have no idea any longer what the statistics are. I think it peaked around the mid-2000s, and then towards the end of, I think, 2008-9 timeframe, several competing bits of software came up, some sort of using a similar approach, and others going back to earlier approaches, as this infrastructure of IT changed significantly. That time, CF Engine was designed in the world where workstations and servers were kind of standalone things. And there were thousands, tens of thousands of them at a time. And perhaps one or two people were responsible for managing those thousands or tens of thousands. But then something crazy happened. The internet took off. It was e-commerce. Suddenly every student and their dog wanted to get a degree in computer science, learned to make a website, and there was, suddenly the market flooded with new talent in IT. And of course, that meant that a lot of people who didn't have deep knowledge of systems came into using computers. So these systems were designed for people with knowledge to express their needs and wants. Sort of went a little bit over the heads of the newcomers. And at the same time, they had skills in programming, so they wanted to make their own things. They wanted to design their own systems and started to create new systems of their own to do this. And with this, the rise of cloud computing, suddenly everybody could get hold of computers and develop software in a very easy kind of fashion. So, in the mid-2000s, you could go to literally anywhere that had computers in the world turn over a rock, and underneath it you would find CF Engine running on that computer. And to some extent, it's still true today. The giants of the industry, who shall not be named, many of them still have CF Engine running in their enormous data centers. So the footprint is there. But the people actively using it sort of in a strategic way are probably far fewer today, because there are many alternative ways of dealing with the managing of systems, in particular cloud computing. Has kind of changed the way that we interact with computers. And it's become much more manual again, because there are far more humans to do those jobs. And humans love to get their fingers in the pie and mess around with it. So there's been sort of a backlash against automation in some areas, where now developers want to really have control again and push all the buttons themselves.
Yeah. The other thing, which maybe isn't as much as an accidental discovery or an accidental venture that you got into, like CF Engine, is promise theory, right? This is a big theme that you've been developing over the years. Maybe you can explain it a little bit to us, so we have a chance to understand it, why it is something that people really need to know about and why it is so important.
It's yeah, great question. But a promise theory is something that I didn't intend to create. It just I sort of stumbled across it in an attempt to understand the monster I'd created in CF Engine. And when I made the software, it was very intuitive. I just kind of had some intuition about how this kind of artificial organism-like thing should work, based on my background in physics. My background is in theoretical physics, and I tend to see the world in terms of equilibria, things in balance, forces, fields of influence, and so on. But when I shifted from physics to computer science in the mid-90s, I spent maybe 10 years realizing that the way that we understand systems in physics doesn't fully apply to the way that we understand systems in computer science, for a number of reasons, which we can get into, I'm sure, a bit later on. But one of the distinctions, for instance, is that in physics, we try to quantify everything, and we're looking at averages over time and over space. We look for variations and trends and things like this. Computers are not really smooth like that. They're very, sudden jumps. They're a bit binary, the ones and the zeros. But things tend to be on or off, here or not there, in this location or in that location. They're very discrete things. And that smooth variation, the way that we describe that in physics, doesn't apply. So I spent 10 years unlearning all of those methods that I was hoping to apply to understand computers. And eventually kind of studied how to understand some of those quantitative things in a different way. But when I'd finished all of that and actually written a book about it, I realized that there was a huge topic that was missing from computing, and that was what it is we want technology to do. Because, of course, nature doesn't have a purpose, and society doesn't have a purpose. It's just doing its stuff, it's doing its thing, and different things emerge from that and may become sort of popular or not popular. So there are shifting focuses on things in these traditional studies like physics and sociology and economics and so on. But in computer science, things are much more deterministic, much more determined. We want this to be running here. We want to solve that particular problem. We have this goal, this problem we need to solve, and here's the outcome. Here's the task to be done. So we have specific desires or intentions that we're applying this tooling, this technology to. And that sort of desire element is totally missing from physics. Physics doesn't desire anything. So how do you describe that? How do you encode that? It's not something that is part of physics in the same kind of way. So I needed to come up with a way to describe that intention that we have for systems, what it's supposed to be doing, and then the extent to which the thing that we've made, the monster we've created, is aligned with that purpose or not. Is it total chaos, or is it very, very precisely tracking our intentions, or what is it? And promise theory was kind of, after struggling for a couple of years trying to figure out how the heck to describe this, venturing into game theory and graph theory and a bunch of other things, and logic, all different kinds of things I really looked into. I realized that there was no story in computer science that was really suited to that problem in just the right way. A lot of things were sort of getting there, but nothing was quite right. So I ended up coming up with this notion of a promise, which is a kind of an idealized version of the promise that we have in day-to-day, which is an expression of intention. I promise that this computer will compute this job by the end of the day, or I promise that it will be running this program and it will be available for downloading this or that, or whatever the specific intention is. We need to be able to encode those intentions into.
I'm sorry.
Bless you. We need to be able to encode those intentions into the system so that we know if we're on the right path. And if we're not, we need to course correct.
Yeah.
So there's this notion of drift. Systems go along, they tend to drift off the path that we would like them to be drifting along. And also they tend to drift from their state of health, their kind of average state of repair, in which they are doing, they have all the things necessary to complete that task. So there are two ways a system can drift. It can drift from the intention we have for it, and it can also drift sort of dynamically because it's a bit feeling poorly or unwell, or it's full of garbage or inundated with other stuff. And we need to be able to course correct machines in both those ways. So promise theory was a way I came up with to describe that. Later, of course, as time went by, we realized that probably because I'm a physicist and I tend to make things as general as I possibly can, I constructed it as a model of agents, which could be things, people, machines, programs, anything. And so it applied equally to humans as it did to machines, or any kind of bit of technology. It could apply to a book. What does the book promise to tell you by the end of the final page? So we can apply the notion of promises to any kind of entity, human, machine, or otherwise. And then promise theory describes the interactions between these things in a kind of physicsy way. How collaboration ensues once you have these basic promises, which are a bit like forces or charges in physics, that allow you to understand how these things can come together and work together to form systems that are larger than the sum of the parts in some sense. And this sort of came about at just the right time, because as systems were scaling on the internet, people needed to solve exactly this problem and realized that these issues were missing from the classical ways of describing software. So promise theory began to get a bit of attention, slowly at first, mainly in the practical folks, the engineering people in IT, not so much in theoretical computer science. Academia, as you know, is very slow to change and a bit indignant to change if it's not one of their own ideas. So that's been slower. But gradually this notion of a promise has found more and more applications, both in IT, study of money, economic models, and even lately in more socioeconomic things and studies of leadership and how companies organize their agile development and how companies organize lean resources, et cetera, et cetera, et cetera. So it's really a very general story about processes. and I like this term processes because it appeals to my, my inner physicist. If we can reduce everything to a kind of an abstract process, whether it's executed by a human, a machine, a book, a collaboration of animals, whatever, the jigsaw puzzle of how we put all these things together is the thing that promise theory tries to describe.
I think this is amazing. And I think looking back, I feel like, why isn't that the cornerstone of economic theory, especially? That's kind of where I see it applicable initially, because maybe that's the one I understand the best. The first thing that comes to mind when you told me about promise theory was Ethereum, like this part of the blockchain that specifically sets out to have an additional contract. So it's not just the token itself, but there is a smart contract assigned, and this smart contract is smart means it's just machines can read it and understand what it is. It's not necessarily smart. We could say it's the unsmart part of a contract, but it is a covenant that you form, and it gives you access to resources, whatever those resources are. And I always thought, isn't that a neat way to kind of describe or tokenize the way how the real economy works, right? How real capitalism works. It's this amazing supercomputer of price information, and then we shift resources around based on this price information. And I feel like there isn't a lot, maybe there is, and I'm just too dumb to read it, but there isn't a ton of research that really goes into this supercomputer that has been running on in our minds for hundreds of thousands, or at least 100,000 years maybe. We don't need real money for it. We just need like some kind of exchange medium. Is that what promise theory in economics has been used for, and people have made new discoveries? Or how does it apply to economics from your point of view right now, when you've seen it, maybe other people have picked up?
It's a humbling experience to try to apply any new idea. I recently realized that it's pretty daunting to imagine that anyone could contribute to any field of knowledge today, because so much has already been done. There are so many people out there working on these things. Anything you try to imagine has almost certainly been imagined by somebody already somehow. In terms of promise theory, it's early days, especially in economics. It's been far more widely used in IT. Let me just mention a couple of things that are characteristic of promise theory. One is that it's a model of agents that are working somehow autonomously. By autonomously, I mean independently. An agent can only promise something on behalf of itself. So I can't promise something on behalf of you, because that would be imposing on you, and you may or may not be willing to comply with my wishes. So people can generally only promise about themselves and their own capabilities. And that fits very neatly with this idea of agent-based systems, the blockchain, the idea of independent actors collaborating entirely voluntarily in an economic or socioeconomic situation. And to some extent, this was the model that Bitcoin and the blockchain folks tried to capture with this model of crypto ledgers. There are all kinds of technological implementation details that I don't want to get into, but they kind of spoil that to some extent. But the idea that essentially all promises originate from self and then need to be understood by non-self, the outside world, is kind of the essence of economics or socioeconomic collaboration, voluntary cooperation. And I think of it as the default state of all systems. In physics, we have this notion of locality, that everything that happens in a system is kind of localized in a particular location and doesn't stray too far from that. So a change that happens here doesn't have a sudden effect very far away from it, typically. That's not entirely true, but it starts from that principle. And in a similar way, when I make a decision about myself, it doesn't have ramifications for the other side of the world without some in-between process that propagates that from one side to the other. And so this idea of things being very localized is sort of at the root of it all. Now, the blockchain tries to capture some of that by making individuals independent, trying to remove the notion of a bank, which is something like a relay hub in a network. Banks act as kind of the routers and switches of the economy. When you send money out, they will accept your money and route it to the next location and so on. So the banks sort of present the world of money as a kind of network in which money is a kind of promise. If you look at old currencies like the pound in the UK, it still contains the text, "I promise to pay the bearer on demand the sum of £1," which used to mean that you could take this piece of paper to the Bank of England and get the amount in gold equivalent to that. Doesn't really mean that anymore, but it's still somehow the promise of value that can be exchanged for something else, assuming that everyone else is along with that game. But it's curious that because of sort of for historical reasons, if you like, which perhaps go all the way back to Moses and the Ten Commandments, we have this view of the world which is based more around command and control, and the idea that if I do this, that must happen. So I push this button, that must take place. I give you this money, you must give me this thing in return. It's entirely the wrong way to look at the world, but we have this kind of bad habit of phrasing things in that way. When I was coming up with promise theory, I was fighting against that model of description of systems all the way. And I think one of the things that people picked up on in the economic realm was also this fact that it describes cooperation from this voluntary perspective, which is more realistic, rather than this force-based push must happen kind of idea that, if interest rates go up, it must be true that this will be the effect on the economy. It doesn't happen in that way, of course. And there's a story around statistics and scaled effects of all those tiny changes happening, which may eventually lead to some of those things effectively happening. But that's a totally different kind of probabilistic story on a different kind of level. And yet we need to be able to describe the one from the other, microeconomics and macroeconomics and vice versa, if you will. And in a similar way, the tiny changes on one computer to the totality of computation in the cloud, or the idea of a single idea to the whole of human knowledge. All of these are scaling problems that we need to be able to understand. And that's something that physics has a long history of being able to explain. A lot of good techniques there to draw on. But the same techniques haven't really been drawn on in the same way in these other areas like computer science and economics. So the folks at the Federal Reserve and so a little group of researchers that sort of stumbled across promise theory and the work I did on describing money as a network, they've been kind of interested in other ways that we can use this to describe a new way of describing economics based around these principles, which is perhaps more realistic than these neoclassical economics of Milton, Friedman, and company, which are largely used by the wider world. And I think it's possible, but no one has really shown exactly how to get that far in that area. It's still a thing to be done. It's certainly true that the way promises work is very closely related to these cryptocurrencies. Ethereum, as you mentioned, can be considered sets of promises encoded on this crypto ledger, which, for better or for worse, are sort of immutable and will continue to be promised forevermore once you've made them, which is both useful and terrifying at the same time. So promise theory gives you a way to describe those things and understand the complexities of them and analyze them. There remains a huge effort to apply it to those things and really decide whether or not it teaches you anything new or not.
Yeah, when you come to a new discipline like that, and you're a trained physicist, and I think also computer scientist, you have a degree in computer science?
I have no degree in computer science, but the majority of my publications have ended up being in computer science, and my professorship was awarded in computer science rather than in physics at the end of the day, because I'd sort of made the switch and had gone into that field. So
When you go to a new discipline, and we know that is something that a lot of thinkers who think more lateral, who are not boxed into specific research or professorship, who have that ability to look outside the box, they do complain about this compartmentalization of science, and that you find it incredibly difficult to go from one discipline to another. And even mathematicians have trouble really breaking into physics, and physicists into math, which seems incredible because both disciplines seem extremely related. To the outsider, they seem almost the same many times. And is that something that you found true as well? And how do you deal with this if it isn't as accommodating as you wish? How do you walk around this?
it's actually terrifying how hard it is to flip between different subjects, even when they're quite closely related sometimes, because there's often a jargon associated with the subject, a way of formulating problems which is sort of traditional perhaps, or closely related to common practice or whatnot. And there's also an enormous stubbornness in people in one field to not think, to see themselves as sort of special, and everyone has the kind of their own special needs and knowledge, and they don't want to be reduced to a general case of something else. So there's often a lot of resistance from die-hard academics in one area to see what they do as being related to something else that they don't do. And ironically, you would think that academics might be more open-minded in that way. It tends not to be the case. But I do find it hard myself. But I've also come to, it's something that I need to do on a daily basis, because I've got my finger in so many different pies that I'll work for a day on this problem, and then suddenly I'm working on a totally unrelated thing, which I find both extremely challenging and extremely rewarding at the same time, because I often learn lessons about both things by being in the frame of mind of the other while looking at this apparently unrelated problem. I will see it in a new light and suddenly realize, oh, you know what? I do know something about that. It's just like this other thing over here. Convincing other people of that connection is a lot harder than seeing it for yourself, I have to say. So it is challenging to take on board and to convince other people of. And this certainly applies when trying to publish results, because journals and academics, or journals tend to be tied to sort of academics who are quite powerful in their fields, and they've won their fame by being successful in one area. And if you try to publish some new idea which doesn't fall into that sort of classical view, they may oppose that for political reasons or for human reasons or whatever, or simply because they don't follow or understand it. So it can be enormously challenging. I find those cross-disciplinary projects that I've worked on have been the ones that have taken longest to gain acceptance, but they've also been the most rewarding ones that have had the greatest impact, perhaps, and the most applicability in the long run.
Yeah, I talked to Patricia Farr, and she just wrote a book about Isaac Newton. And I asked her about, is the age of the polymath coming back? And she was very skeptical. She's like, this maybe, but there's nothing that suggests this right now. So if anything, it goes the other way right now, which doesn't bode so well for people like us. I'm definitely far away from the depth of science you do, but I consider myself a generalist, and that is definitely, well, it's not a skill that's as much in demand as I would hope. Let's put it this way, or maybe that's just me, right? So there's a lot of avenues there. The newest thing you work on, and you wrote a book about it, a popular science book. and it's called Smart Spacetime, and it is about semantic spacetime. Both are terms that I've never heard before we actually talked last time. What does that mean? And is that something that changes Einstein's theories? Is that a quantum dynamic physics book? Should we think of when we hear the term smart spacetime?
So Smart Spacetime was the popular version of Semantic Spacetime that I used for my book because I thought it would be easier to understand. And it turns out to have some connection to artificial intelligence, and perhaps even our notions of consciousness and so on. But let's not begin at that end. This is also something that came out of promise theory and my attempts to describe ordinary processes in widely different scenarios in terms of this idea of the cooperation of independent agents and independent pieces coming together to form a whole. Now, if you imagine, an agent is a bit like a person. It could be any kind of person. It could be an atom. It could be a person. It could be a nation state. It could be any kind of a cell in a body, an animal. Basically, the thing that characterizes all of these systems, if you want to call it that, at different scales, and to very different, in somewhat different ways, but just go with this sort of general idea for a moment. The thing that characterizes all of these things is that they are entities, sort of localized entities that receive input from outside, information from outside, and they process it in some way, and they may respond in some way by giving message back or generating some output, making a promise, a new kind of a promise, delivering a service, and so on. So an atom may absorb a photon, it may emit another photon, or it might interact with another atom to form a molecule. The molecule might interact with another molecule and form in such a way that it be, for example, a virus. It may infect a cell. The other one might be a vaccine, which sort of neutralizes the virus, or an antibody which neutralizes the virus. So all kinds of entities can be considered from this point of view that they both do things and they have some kind of a purpose or an intention of some kind, which can be aligned with. And then the way that we combine all these alignable intentions forms a kind of chemistry, which again allows us to combine them into new things, and those new things can make new promises. Again, they will receive new kinds of input on a new level and generate new kinds of output on a new level. So no matter how primitive or sophisticated that kind of model is, there's something similar, which is a system which receives something, processes a little bit, and spits it out again. And what happens in between is kind of interesting. Of course, depends on the resources inside this agent. Does it have a complex brain with a lot of memory, or can it only remember a single bit, a 1 or a 0? So the degree of sophistication matters a lot. But the reason this is interesting is part physics and part computer science, if you will. And the physics part of it is that, we don't really describe physics in that way. The way we've learned to describe physics since Newton's time, Galileo and Newton, told us that we have bodies, entities, particles, if you like, and they tend to move in straight lines. And then they hit other things and they move off, and you follow these lines and you figure out what's going on. This concept of something being inside something else, or something arriving at a location and being absorbed, processed, and emitted, isn't part of that story of physics. Or it wasn't, at least until the quantum theory came along, and then suddenly it became important. And so there was this kind of missing perspective in the way that we try to deal with physics. And if you look at the way people tried to deal with quantum mechanics, they also tried to start with this notion of things going in straight lines at certain locations and so on. And they got into a lot of trouble with that. So it took a long time to figure that stuff out. On the other hand, in computer science, people have this very centralized notion. You have a computer, it has input from the outside, and it generates output. It's clearly centralized in a location. Similarly, with biology, you have cells that absorb and emit. You have organisms that are centric, that receive sensory information, process it, and change behavior as a result. And so this centralized view of the universe, almost this Earth at the center of the universe, the Copernican revolution, that story was eradicated from physics to its detriment in some respects, because we've forgotten how to understand systems in that way and go between that to this more straight line version of description. And yet, all of the interesting things that happen in the world are based around these more centralized configurations of information coming in, process information going out. So I wanted to see, we describe space-time, not in the way that Newton did, as a kind of a theater in which things move around, and which Einstein took and corrected to add back some of those details which don't work out quite right when you don't take that centric thing into account. Could you redescribe space-time by building it up from the ground level out of agents with the promises that they make, more like a network? So again, you end up with a network description of space-time rather than, as we had for the money, for the economic story, rather than this kind of empty space with matter floating around in it. What if everything is simply part of a giant network, and all of these material excitations are just bits of information running around the network? Could you describe the world in that way? When you do that, it allows you a neat way of combining the semantics, the meaning, the interpretation of things with all of those dynamical behaviors. The qualitative and the quantitative come together much more naturally in that framework than they do in either the Newtonian view, which tends to eradicate semantics, or the centralized universe, or biological point of view, if you will, psychological point of view even, where everything is centralized and this more objective view of the world is demoted. So this constant tension between subjective and objective in the world don't go very well together, except in premise theory, which unites them in a fairly natural way. So I wanted to put those things together and try and describe space-time. And the interesting thing is that when you do that, you have a story which, although varies wildly in the details from the very small to the very large, remains essentially correct, whether you're considering an atom or a country interacting with another country, or, for example, a human brain, a conscious brain. And it tells you a little bit about the necessary and sufficient conditions of what must be going on inside in order for certain promises to be kept on the outside, which I think is powerful. Of course, it sounds very easy, but it's very hard to go into all those details. So perhaps I make it sound easy. It's not trivial by any means, but I think it's a story that needs to be taken seriously. And so I wrote this little book trying to explain that point of view.
It sounds fascinating to me. And I feel like these two views on the world, as you outlined them, they've vexed me too. This one part of the world where we feel, even if we can't really describe it in technical terms, there is a purpose, there is a reason, there is a creator even, right? Something that definitely has already an inbuilt direction in life. And I know you've been quoting Goethe's Faust on your homepage. So he's been pondering with the same question. We clearly feel, although I don't know what science did in the last 200 years, but we clearly feel there is this positive direction of the universe, and it goes somewhere. Even if the individuals don't know where it's going, these are all part of this machinery. They are not just a cog in the machinery, and to an extent they are, but they all follow a certain direction, more or less. And then we have this, as you say, this whole objective universe that is basically like cold, and it doesn't have any direction. It's just there. And I find, and you must have thought about this, if you go keep and if you keep this further, why is the universe there, and is there a creator? And well, that would be the first question I would be drawn to when I would think about that theory. And you must have done this probably decades ago. What did you find? What is your gut feeling?
I think we have no way of answering the question, why is the universe here? To do that, we would need to somehow to be outside it, and we don't know how to be outside it, or if there is indeed anything outside of it. We don't even really know where it comes from, although we have a lot of stories that are consistent to some degree with things that we see within the universe. We are trapped within this universe, so our ability to get outside of it and understand that part is pretty limited. There are still certain things that we can say about how it might have arisen. But when it comes to purpose, this is an interesting question for me, mixing together these two sides of my work, which is the physics, as you say, very objective, and the information science, which is to some degree more subjective and intention-based, and relates far closer to things like human intelligence and consciousness and so on, all of those ideas. What physics teaches us is that the world is very different at different scales. We tend to try to look at the world from our scale, our human scale, of course, because that's what we know. And we're far better rehearsed at understanding the world from that point of view. Sometimes that means that we impress upon the world things that aren't true on other scales, and we make mistakes in the way we reason about it. So, for example, we should never try to imagine that an atom behaves anything like a human being, or that a galaxy behaves anything like a human being. And yet we know that the rules of interaction between things on those scales still have certain similarities. There are still things to have with inputs and outputs and things that happen in between. So you can to some extent use knowledge from one scale to infer what might be going on at other scales. And in physics, there's this notion of dynamical similarity, which expresses that point of view. It's also called scaling. Newton would have called dynamical similitude, is the idea that similar systems may have similar explanations, or similar phenomena may have similar explanations in some sense. And to get it right, you need to adjust all of those ideas, to make sure that you're not kidding yourself. But it's basically my belief that that idea can be extended in the way that we do in physics, which is purely quantitative, to the qualitative level as well, where semantics can also be scaled in the same way that we can scale processes. And when you do that, you start to see things in very interesting ways. The ultimate expression of that, I think, sort of the greatest possible outcome of that would be somehow to understand our own ability to have a conscious understanding of the world around us. Some people think that's impossible. Some people believe that there's, consciousness is something totally different from what happens in the physical world. I don't believe that. I believe that we are just cogs in a machine, but that we just haven't understood the extent of machinery in all of its glory properly yet. We tend to imagine that machines are more limited than they probably are. They must be. From my point, I take it as an axiom that we are machines, and yet we're nothing like, machines that with cogs that we turn a handle like a car. Totally different animals, things. But nevertheless, there are processes that take place in these things that can be described. Now, one of the things that changes when you jump across large scales is that systems no longer are deterministic. You push the button or you turn a handle, the response of the system isn't 100% exactly as you hoped as you scale systems. it may only be halfway, or it may only be a probability, only a chance that turning the handle actually leads to the outcome. And that's not counter to the idea of machinery. Lots of machines also behave in this way at scale. Take, for example, the global chain of logistics chain, where we transport goods around the planet. You place an order for a new car, and it sets in motion a bunch of processes that result in a car being sent to you. But you have no way of predicting exactly the time between you ordering the car and the car arriving at you. It's an entirely non-deterministic thing. Even being able to trace its progress around the world on shipping containers that may or may not get stuck in the Suez Canal, that's a totally unpredictable thing because there are far too many variables to take into account. And the way that we see the world is not like the Newtonian picture in an enormous theater in which everything is precisely deterministic. It's a subjective observation, much more like Einstein's view of the universe and much more like the quantum view of the universe, where the observer has a very specific point of view, a very privileged position, but has limited access to information. And it's that incomplete information which makes the world unpredictable in our eyes from our perspective. If you could imagine some kind of godlike observer as Newton did, his entire approach to physics was based on his belief in God, that there was a creator who could see everything instantaneously. We know that that's not true when you're trapped inside the universe. And on different scales, you have to deal with different kinds of delays and different kinds of challenges. So we need to take that into account as we scale systems. If you do that, you find that the world behaves actually with quite predictable regularity. But by predictable, I don't mean we know precisely and deterministically what's going to happen. I mean that we can generally write down some kind of a prediction as to what may happen and constrain that to some degree to make a kind of prediction. I think we can do it in almost all cases. And I find it fascinating that that is still possible regardless of the scale. The place where people often get stuck and tend to object to this kind of view is the question of free will and consciousness in humans. And I find this story fascinating. I've thought a lot about it myself, and I believe it to be related to this notion of smart spacetime, that if you could put a boundary around sufficiently complex resources and sufficiently complex processes on the inside of your head, basically, right? Then all of those things can be made to work in the way that we know that consciousness works. And this kind of belief that those human aspects are somehow special, emotions, point of view, personality, that they are somehow not machine-like properties. I don't believe that for a second. I believe that all of those things are highly natural parts of the processes if we only understand them in the right way. So, for example, as we were setting this up, we were talking a bit about AI and what might be the next stage of AI. Some people think of artificial intelligence as being the intelligence whereby we eliminate human emotion from the equation. If you look at the history of science fiction, there's this fascinating notion that, when the robots become super intelligent, they will be devoid of emotion because emotion is a weakness, a human failing. I believe that that's exactly the wrong way around, that it's those emotions that lead to things being more important in one individual than in another individual, that amplify and settle the question of should I or shouldn't I, will I or won't I. It's those potentials that arise in individuals in different ways because of the different subjective processing of information that leads to precisely those things, the uniqueness of the individual, and all of those things that we tend to associate with humanity. So any story about artificial intelligence or the processing of knowledge that excludes the concept of emotion, I think will fail miserably to recreate anything like what we imagine human intelligence to be.
I'm fully with you. When I think of these parts that we can't explain in the human brain yet, like emotions, where they come from, how they're being inherited, I mean, there's lots of them, consciousness, what morality, ethics, right? I feel like when we talk about artificial intelligence, those are all survival mechanisms that have made us a more successful predator, a more successful animal, so to speak, right? So that's why we rose beyond what else is out there, and we actually have a successful story to look back to the last 50,000, 100,000, 200,000 years, whatever we want to count. And I don't think that an artificial intelligence, whatever the way it looks, will be able to live without any of those systems. Yes, they might leave them behind and go to higher systems relatively quickly. So it might not be 50,000 years, it might only be 50 years. But they will go through the same problem of what are our values, what are our ethics, what do we prioritize, how random are we, as you say, that's what emotions do, how do we derive an ought from an is. That is a huge problem, and each machine will have the same problem in a hive intelligence or not. And our algorithms that we evolved, which seem to be the best on the planet, we seem to have that impression right now. I think with a good reason, will develop in machines too. But I think what comes next is the problem is that we have things like GPT-3 who were designed for something completely different, and it wasn't like a big deal. It wasn't like such a great endeavor. It was a few $1 million, but it wasn't like, a Manhattan Project. But it suddenly could do poetry, it could do HTML code, it could do Python code. And even the developers were really surprised, shocked maybe, what it could do. Now it's still very elementary, and it has a different approach than we would assume. And it doesn't have any of these advanced things we just thought of. But what people feel like there is this tomorrow, someone in China comes up with an artificial general intelligence or a super intelligence or human-like intelligence. It's difficult to find those words. And yes, they have emotions, and yes, they have consciousness, and they will act like us. So that's all good, and I think we all agree on this. But only, 10 years later, there's something out there that is like on a scale of several billion smarter and better developed, that has all these things that we've developed, but it's like so far away from what we can see as the most smart human on the planet right now, that we barely have any words. And the worry is a little bit that this scales up in a very small time frame. So we can't see it progressing because it's so quick in learning, because that's what we attribute to machines or machine learning. That might not be true, and I hope you can tell me better. But that within a short time frame, maybe within our lives, and people think about singularity as a popular science word for describing that in, say, 40 years, machine intelligence is so far out that they have all this what we know, but they have so much more that we can't even understand them anymore. We don't know who that is. They go to the stars, and we can't even send them letters.
There are already today plenty of systems that we can't understand. So I think that's not the benchmark for creating machines that we can't understand. I don't believe in this notion of the singularity for a simple reason, that it is a story, again, based on the prejudice of human scaling. It doesn't take into account the scaling of the world as we understand it. It assumes that if we create a giant computer system filled with all the information we can feed into it, we feed all the Wikipedia into it and every bit of human knowledge that we can find, that it will somehow behave like us. But think about what makes a human like us. We are the way we are because we're surrounded by people like us. We went to school with people like us. We learned slowly over time, running around a playground, climbing trees, and doing things that humans do on a very specific range of scales. Computers have no access to that world. They don't have a sensory apparatus for running around climbing trees. They download information in an entirely different way from bookish sources, right? You can't learn to climb a tree by reading a book. You do it by imitating a physical process and mimicking certain behavioral motions through actuators that behave in a very particular way, creating a specific kind of information stream that we are well adapted to. It would be, first of all, it would be nonsense to try to recreate all of those things in IT. No one would do it. Even if you could do it, you wouldn't be able to get the same information to train it without, literally creating a robot the same size as a human being and sending it to school in the same way that a human being goes to school to learn to even care about us and our world.
But our world has changed so much. I feel like we've cloudified ourselves so much. Who reads a book anymore? Nobody. I mean, nobody under 15 ever reads a book, right? Yes. But think about the generation that's growing up right now. Who still climbs a tree? It doesn't exist anymore. These kids are literally in like a machine in a display in front of their head, and they don't move for 12 hours a day. That's it.
Well, now you put your finger on something very interesting, which is perhaps not so much that we should worry that artificial intelligence may exceed our best human beings, but rather that we might be turning our kids into robots by turning them into cyborgs, by sticking their heads into these things too much of the time, and getting everything at the push of a button, where, instead of needing to use our manual dexterity to create something, to use our minds, we simply treat everything as an ATM where I want a pot of noodles, I push the button, it arrives on my door, like the Star Trek food processor.
Wait, you don't have one of those?
Everything we want at the push of a button is the quickest way to retard our intelligence and go backwards. Because if we no longer need to be creative, if we no longer need to connect together dots, causal events, then we're not exercising those things that our brains evolved to solve. My belief is that the essence of intelligence, not so much intelligence, but, well, consciousness, if you will, is essentially a thing that our brain does to tell stories. If you think of a brain as a kind of computer, it's not a computer like the ones we have, but it's got a bunch of memory. And that memory isn't moving. It's, some bits and bytes stored in some cell connection somehow. But in order to recall those things and create a dynamical picture, like, for example, when we're dreaming or when we're looking around us and seeing things changing in real time, to create a real-time picture from static memory, you need a process that generates stories, tells stories, a narrative process. And that's the piece that we're missing today. We know how to take information from the outside, pattern it, and store it in a static way in order to compare to patterns, detect fingerprints, faces, etc. So we know how to do the things that eyes do, and the parts of the brain that decode the patterns that senses decode and turn that into static imprints. We don't yet know how to reconstruct dynamical worlds from those memories in the way that we do when we're sleeping, for example. When we're asleep, the main difference is, brains are very active. The main difference is we're cut off from our senses to a large degree. And so the things that we're imagining can only be coming from the memories inside us. And yet, what bizarre things that we dream, and it seems so real when they're in the moment. You don't question the reality of it when you're dreaming. Only later, when you compare it to the world that we're more used to, anchored in reality, do we start to question, oh, that probably wasn't real. It's a different kind of thing. But that illusion of reality that we experience in dreams, I think, is the crux to understanding our conscious understanding of the world. The ability to tell stories, and that again comes back to this promise semantic spacetime idea that we need to combine dynamics with semantics, patterns, meanings with changes. And that's how we create stories. That's what we mean by stories, right? A stream of semantics is basically a story. So that's, I think, the great challenge for us to approach some kind of a generally intelligent whatever that means, organism. And I think it'll take a lot longer than 40 years to get there, because I think we just don't understand scaling in IT. There are two parties looking at this question. I read a lot of books by both of them. So on the IT side, you've got all the AI folks believing that the neural networks have some magical mystery that will just sort of make it happen. I don't believe that for a second, because they don't understand scaling. And then you've got physicists, on the other hand, all these usual suspects who fall straight into the trap of physics envy, wanting to talk about entropy and information and quantum computing and all of these things. I don't believe that's got anything to do with it either, because that's about an entirely different level, entirely different story, where semantics have no place. So unless you unify these two pictures, the semantics and the dynamics, in something, call it smart spacetime or semantic spacetime, if you will, basically agent models and networked structures, network structures, the ability to constrain and allow freedoms in a constrained way around localized processes, individuality, different viewpoints, all of those things have to come together. Then only then will we start to understand what we think of as consciousness. You know,
a lot of people would say, well, when we talk about meaning, it's literally just, and I know this word doesn't fit there, a compression and an indexing algorithm. So instead of saving the whole image, which is maybe, say, 1 gigabyte, a big picture, or a couple of megabytes, we just say, well, that's a picture of a dog, and it's a happy dog, and 15 other attributes. So we just compressed it from a huge data set to a really small one. So that seems to be something that's going on in our mind, right? So we save the shapes, and we save certain semantics, meanings, attributes, and then we have an imperfect indexing algorithm. It seems to be something that is relatively obvious to be solved with artificial intelligence, because it's good at tagging stuff. It's good at compressing it to a very small number of attributes. And once you have a model, that's the fascinating thing. You can apply it once you feel it works for what you want to do and for your data set. You can apply it anywhere you want. It's really cheap. It's really fast processing. It only takes milliseconds. But building the model takes a long time. And that's kind of what when we describe ourselves as humanity, we build the model that takes forever. But once we figure out what we want to do and how we classify things, it's relatively quick. And I think this is why artificial intelligence researchers right now, on one hand, they know what they do is just pure statistical models, and it's really boring. There's no consciousness into it, but they feel like once we make that step that we can basically classify everything and compress so much, then the next step comes in and we have like this next level of AI, or maybe a slightly different technique. And we feel like, well, even with relatively limited amount of space, we can make sense in the sense of we can make a probabilistic description of what this could be, and we can predict the next steps. So when a cat, you know what the cat probably does. It's an easy model to do. And that seems to be something that even children have. They know they can distinguish spiders from cats, for instance. And you don't even have to run them through a big model. They come with the model already. It's in their brain when they are born. Maybe they learn it over time. But it doesn't seem to be such a big stretch. And then to assume that we can describe the world and build an intelligence that can go through the world kind of like we do, but an imperfect model. It's never going to be perfect. We add some error correction like we do for children, right? Don't touch the oven, it's hot. They figured this out pretty soon, not to do this again. Attention model. I feel all the switches are in place to get to something that resembles consciousness, even if it doesn't have consciousness. But then again, we look at people, the scale of consciousness in humans is pretty enormous. Like we find people who are pretty obliterated to what's going on in the world. They have no clue. They don't want to know about it. And then we find other people philosophers who spend day and night just, sharpening the knife of consciousness. So there is a huge scale. But if we say we just want to build an AI that for now works like a, 8-year-old, I don't think we're that far away from it.
I think you touch on an important point, which is that a key aspect of processing information is the ability to compress it into tokens or symbols, symbolic. And there's this artificial distinction in AI groups between symbolic AI and non-symbolic AI, or neural networks, typically, machine learning, if you like. I don't see those things as being distinct. I see the machine learning tools as being ways of compressing information into certain representations, some of which are smarter than others in the sense that they can adapt or embody variations in a more interferometric way. It's kind of like interferometry. And the mistake, I think, is in believing that you can reduce all of the cats and catness to a single symbol or word, and it's like in a book, you read the word cat, your mind immediately thinks of a million cats and all the crazy things that cats do. But there is no sense in which having gone in the one direction allows you to go in the reverse direction. We don't know how to do that yet. And I think some of the most advanced brain researchers of today are starting to talk about the brain not as being something which is mainly fed by inputs, but actually something which generates the world from within and rather anchors those imaginings, those processes on the interior, anchors those things to sensory, interferometric sensory inputs, combinations of sensory inputs, and then tags those things in some smart way. Of course, we don't know how it works yet. And the ability to generate stories and recreate those worlds is, again, part of the problem that I think is missing. But it's a really important thing that a cat it's not a symbol, it's a process. The cat process, it's probably more like a living thing in our minds than it is a static memory. And I don't believe we've begun to tackle that problem yet. Yeah. My hobby is, ever since I was a small kid, the first thing I ever wanted to do in my life was music. I was always fascinated with the orchestra and the way that an orchestra comes together from all of the individual instruments. And each individual player is playing with great skill and great individuality. But the sum of all of those processes creates music on another scale, which is the symphony itself. It has a lot of interwoven parts, themes interweaving with counterpoints, and all of these complex musical things, which I love to do as well. I compose music as a hobby as well. But I see very much physics, information, AI, all of these topics are very much like music in that sense that it's the coming together and interfering of processes rather than bits of static data in a data model being looked up by a machine-like retrieval process. So it's unlike that ordering that car from the other side of the world through the chain of logistics. It's far more like watching all of the cars driving around all over the place and figuring out what's going on, because suddenly everyone's driving to New York for a concert. That's the expression of that thing. It's not a simple symbolic action that could be written down. Of course, you can write down those things. You can always compress. And this has been enormously useful to us in language. So the fact that our brains evolved language, I believe, is connected with this phenomenon that we're able to compress things into symbols as part of the process of cognition. So it allows us to serialize our knowledge and communicate it with others. But of course, throwing the word cat to a person that doesn't know the word cat, totally unhelpful. They have to have a process. They have to have a cat process that they can anchor to that symbol in order to interpret it according to their own understanding and in order for us to resonate and find common ground. And that's the part, again, where AI and singularity thoughts are not really giving the human part of the process enough credence. There is no counterpoint. There's no society of super intelligent computers from which to learn from each other, to build that compositional framework for mutual learning and evolving the symbolic underpinning for that super intelligence model to emerge. And I think that's the bit that we're underestimating or misunderestimating, or whatever the word is. And that will be the thing that we come to solve over the next couple of decades, probably, because it's always slower than we think.
Yeah. I want to go back for a moment to that point you made earlier, and correct me if I misunderstood it, but there is a directionality, it seems. There seems to be a purpose that each individual level that we look at plays. And it seems to be something where we have this time stream, and along this time stream, or maybe that's the in the end the question, it's the time stream of the universe and what happened to the universe. It isn't all random. So it started from what we know out of a small soup of energy, and it created this massive conglomerations of stars and planets and then intelligent life. And there is this book about intelligent design. When we look at just what happened in the early days on Earth, I don't know if you ever looked into this, we have this incredible odds for any life to exist. We can say, well, it's billions of years and there's billions of stars. And so it's in the end a computational probabilistic approach. And we can say at one point it must have happened. But the strange part is that we go from something with very low complexity, at least from what we look at it. Maybe that's the wrong way to look at it. But we have this soup of initial proteins, and we have, well, actually it's just molecules, atoms, molecules, and then they produce the soup and the proteins and the cells. It seems incredibly complex, and it's getting more complex. Do you think there is agents at play? And again, this is probably the question how we look at this level. There seems to be a certain purpose driven to a higher complexity that seems to be innate to the system. So these agents, we talked slightly about that before, about the creator, but it doesn't have to be, is there a designer? Is there, at some level, we are driven somewhere? We are kind of just the bootloader, the wetware to create artificial intelligence. Maybe that's just one more step in this. But it's your assumption when you see this in promises that each of these agents make to each other, that they seem to be, they want to go somewhere. Or is it just randomness? And we see this, the 10 billion years of the universe, they were all just random.
We have this tendency amongst people to anthropomorphize things, to make things, to attribute things human intentions. I think it's actually harmless. Some people get very upset about it if you say, oh, the electron wants to be attracted to the proton. It doesn't bother me at all, because in promise theory there's this notion of a possible intention and a real intention, or an intention that has been adopted by a human or some kind of a mechanism. A possible intention is really just a direction. It's just a way of describing direction in a space of possibilities. So the fact that we as humans can have intentions, possible intentions, or machines can have possible intentions, an electron can have a possible intention on a simpler level. It doesn't require the notion of consciousness or decision-making, free will. So I find that entirely unproblematic. The question of whether there's a God, I also find sort of uninteresting on one level, because I don't believe there's a human-like entity that thinks like we do, looking down on us from outside the universe, guiding things, because any being with those kind of powers would be totally unlike us. We wouldn't recognize it. Just as we may not recognize life on other planets if it's on a different scale from us. There's a sense in which the Amazon rainforest is alive and the trees talk to each other. This amazing work done by German researchers 10, 20 years ago, showing how trees form these networks of communication. Then they're talking to each other with fungi. We don't know what they're talking about or how smart they are, but how would we even know? How would we begin to decode that? We've no way of even connecting with it in the same way that a super intelligent computer might not even see us as might not even see us at all. So these different kinds of entity, whether we call them God, super intelligent computer, life on other planets, it's not clear to me that we would understand each other or recognize one another because we simply are too far removed from one another in the kinds of processes that we are. And yet, if we had long enough and had enough resources, if we could collect that information and see the patterns over time, who knows what we might find? We might discover that the entire universe is thinking about something in some sense. Might not be a very interesting thought, but who knows?
Is your gut feeling, and this is more faith than writing a white paper, right? So I understand the science has a maybe deterministic view on this. When I would ask you about your gut feeling, if we live in a simulation, if all of these things come out of somewhere and we're driven by intelligent agents, so to speak, like each of these agents has an agenda, we don't know it, we can't recognize it, I agree. But I think our human brain, for better or worse, has a certain kind of perception for other people's agendas, and other, as you say, is a very human way to look at the world. In your personal intuition, do you think there is something out there that's guided this whole process, or it's just sheer randomness and we're just this pure little bit of luck that happened on this rock?
I don't think there's something that's guided us on any scale that we recognize. But of course, we still have no idea about the origin of the universe and matter and energy and why it has this particular standard model of interactions. But somehow built into that ability for these key processes, whether we call them electrons, quarks, whatever they are, and the forces between them, whatever created those kinds of processes, that palette of colors from which we paint the world around us,
yeah,
we have no clue where that came from. But latent within that, across multiple scales, the ability to things to attract one another and come together and to represent information and create increasingly complex representations that don't simply fall apart and decay into entropy straight away. The fact that that is possible, we have no idea why or where it came from, but it's latent within that, everything we see around us, which is remarkable. But I know enough of physics and computer science to know that you don't need to invent a mystery about getting from the very small scale to the very large scale. It's, even without becoming a total reductionist, you can say that everything that happens on the large scale derives from things that happen on a smaller scale. But that doesn't mean that there are not new things on every scale that couldn't be predicted from the nature of things on the small scale. Because the nature of information is to decouple across multiple scales and to introduce new levels of information representation along the way. How that ends up producing all of these marvelous things is truly awe-inspiring, and I have no idea where to begin to describe that. But some people find it comforting to attribute that to a creator. I don't. I find it marvelous to believe that this could happen by chance, or if chance is even, because we don't even know what chance means. There's so many things we don't know that it's hard to give a name to that particular thing that's missing from our understanding. But I don't need to call it a god or a designer.
Yeah. If we were ever able to create our own universe, now that's a big stretch, right? So we're talking about hundreds, thousands of years, millions of years, or a long time frame from now. What do you think would be the thing we would most emphasize? What would be, when we design it, when we had the opportunity to design it, what would be the most important factors we really look carefully in a design, and the rest we kind of leave to chance?
Winning. People always
Winning.
want to win.
Like,
We create our own
like
universes,
not
right?
just
We create.
entropy. Like entropy is the opposite of winning, or what would be the opposite?
Well, you define winning however suits you best, of course. We do actually create our own universes, right, in computer games all the time.
Yeah.
They're becoming increasingly sophisticated. Of course, they're nothing even approaching the sophistication of anything in nature, but still there are frameworks in which things evolve, change over time. They're not fully determined. And they have, pardon me, no clear outcome except that when we create these things, we usually want somebody to be able to win.
Yeah.
we
Like a
like to
game,
win,
right?
like a game. I've no idea what the winning move is in the universe game. I hope it's not the heat death of everything, but who knows? I suspect I won't be there to see it.
I'm asking because when we make up our mind and feel, and it's a bit of a religious question. If we live in the simulation, it seems we everyone needs simulations, and we use abstract dot as a simulation, right? Instead of killing an animal, we think about killing an animal, and so we improve our odds when we actually go out there and get in a dangerous situation. Anything that is more abstract than concrete doing is part of the simulation. So we will just keep on simulating whatever we can and just run our odds. And I think artificial intelligence, to an extent, is just an extension of that. The difference between a simulation that we create and if we are in a simulation and we don't know it, maybe it's just the amount of energy, this pure amount of energy that was the starting point of the universe. And then one thing, I don't know what physics thinks about that. Maybe that's something you've looked into, is this concept of time, right? So we know with Einstein that time is very relative, but that's a relatively new discovery. It's only 100 years old, a little bit more than 100 years. Do you think time from outside the universe could be a very different animal? Let's assume for a moment we are in a simulation, and whoever simulates us, for that intelligence, the time would only have been a few seconds, but for us it's 14 billion years. So time could be so extremely relative from different parameters when we look at time.
Absolutely. We know this to be true in the world around us today. It's actually a myth that Einstein showed that all time is, that we can only measure relative times and locations and velocities. And it turns out that I should say that differently. It's sometimes claimed that Einstein proved that there's no absolute position, there's no absolute time. He didn't really show that. He only showed that view of the world is unavailable to us, being stuck inside the universe as we know it. It's entirely possible. In fact, it's easy to show that you can create, we do this in the cloud, the computer cloud, that the time as experienced inside a virtual machine, a virtual process, is very different from the time experienced by the computers that they run on. And the network of computers that they run on they form a kind of an absolute space-time with fixed locations, absolutely not relativistic. And yet the processes that run on them experience relativity in a similar way to the processes that run in our universe, material things moving at relative velocity like Einstein showed. So it's simply a fact of processes running inside processes that allows things to become relative. It in no way eliminates the possibility that there is an absolute universe, an absolute space-time underneath it all that we can't access at present, perhaps one day, but probably not. But it's entirely compatible with the maximum speed of light, for instance, that we simply are running on some kind of process that has limited resources. That finite resources immediately leads to a maximum speed limit in propagating processes. And we're going to rediscover all of those processes, all of that physics again in the cloud, in the computing cloud, as we become challenged with bigger and bigger computer systems, busier and busier computer programs running next to each other. All of that unpredictability and weird, the weird effects of space and time that we see in Einstein's theory, we're already seeing them in the computing world. They just manifest slightly differently, and they're not immediately obvious to everyone where we are, because we are kind of the godlike people looking into the cloud from the outside. We have a different perspective. But from the perspective of processes inside the cloud, they experience the world in a far more Einsteinian way. So, these things, we like to mystify some of these phenomena in the natural world and believe that they're magical, they're special. We will never see the same thing again. Anything that humans create couldn't possibly compare to what we see nature has created. I don't believe that. I think we're seeing them already, just on different scales. And if we, again, pay attention to scaling and dynamical similarity and follow those principles as the old philosophers taught us, we will rediscover the world around us in new ways, in a computational way, as an information world, as we're already starting to do. And we will find new levels of understanding which currently seem mysterious to us.
When you look at some of those breakthroughs and these rediscoveries, when you look at the next 50 years, so time when we are still alive, very conveniently, well, with Aubrey de Grey, this might be a much longer time span, if he is right. He says only 20 more years and then we can live forever if we get the right drugs. What breakthroughs do you think are coming to the field, especially computer science, physics? Physics has had a long love affair with string theory that doesn't seem to produce anything. Maybe it's happening tomorrow, who knows? But from your point of view, where would you feel the next 40, 50 years have a lot of breakthroughs? What could we get at? And we already feel somewhat confident about it.
It's hard to predict the future, of course. I tend to think that the interesting questions lie in this overlap between physics and information, but not in the way that people are talking about now, not in this kind of idea of quantum computing or even blockchain or any of these kinds of technologies. I think understanding the physics of computation as we do it in computers today, not on the quantum level, but certainly incorporating that down the line, because there's so much we don't understand about how computers work. There's this odd myth that computers simply do what we tell them to. It's not true. They do all kinds of things that we don't tell them to do. There's emergent behavior on all levels. You can't possibly describe the behavior of the cloud as we understand it today, or all of the data in the world, without appealing to some sort of weather forecast level understanding of the world. It's utterly unpredictable. And to claim that it's simply a deterministic result or a scaled result of everything we've created is just pulling the wool over your eyes, because it means you've misunderstood some principles about scaling and how new phenomena occur on new scales.
Yeah.
We are starting to understand these principles, of course, in complexity science and information representations and da-di-da. But I still believe there's a long way to go. And people are resisting too much the idea that, people still want, as we said earlier, they still want physics to be special. They still want quantum mechanics to be that mysterious thing that only physicists can understand. They still want relativity to be Einstein's property, and there can be nothing else like it in the world. Until we can get past those prejudices and move on to a new understanding, applying the same ideas wherever we may find them, and be willing to do that, to go out on a limb, to take a chance, I think we won't uncover some of those mysteries. Personally, I'm not a string theory fan or an M theory fan. I don't believe that stuff is, I think it's cool mathematics. We may end up learning some interesting principles that can be applied in a totally different way. but I don't think that is the source of our understanding of the world going forward. We need to get our handle on empiricism again. We need to reclaim empiricism because we've kind of lost that in all of the theory. You know, I'm a theorist from top to bottom, but unless I can get my hands dirty and compare it to something real, I don't believe anything about what I come up with, right? It's only because I've been able to compare the theory that I've worked on with computer systems as they've grown and human computer systems interacting as they've grown. That's how I've been able to see that there must be something in this story around promise theory and semantic spacetime. But it's such early days, you know, there's so much to do to place that on a firmer footing. And I do believe that if we can really understand those principles, we may even find the echoes of things that are totally unavailable to us, like quantum gravity, hiding within our understanding of network phenomena on an entirely different scale.
Eric Weinstein put forward that thought that there might be an entire generation of physicists lost on string theory instead of doing something useful. You know, that's obviously a very strong statement. But I think what he meant is and you just said that engineering in a lot of fields that physicists touch these days is lacking behind, and the cloud might be the exception to the rule. So we had hundreds of years where they kind of went in lockstep, right? So you could come up with a theory and you could test it definitely in your lifetime, probably within a couple of years, month maybe. And then we went out and our simulation, so to speak, of these problems has gone far beyond of what we can actually implement. Would you, from your point of view, do you think that's a problem of engineering because productivity growth has been too slow? We don't have the energy required. We can't just build all these colliders. They're super expensive instead of just, you know, we can build it in our own lab. Or do you feel that's more a problem of misguided directionality of research in physics and related disciplines?
A bit of both, maybe. I think what's fascinating about engineering in applying science to create stuff is that a good engineer doesn't try to develop systems to be understandable. They develop systems to keep certain promises or to have certain outcomes. Yeah. And even when we look at nature, what nature has built from the technology of all these different processes, the quarks and the electrons and the going, you know, through biology all the way up, there's nothing you can point to in that which makes it easy for us to trace the nature of nature, if you will, and uncover those mysteries. It's hard because it's way more efficient to build things that hide that information on each new level. Just as you boil down, you know, terabytes of data into a single symbol or a simple model of a cat, that's efficient. That's what technology is about, reducing the information down to small amounts that can then be the basis of new virtualized processes, which is what we understand as engineering. But because of that efficiency, it makes it really hard for us then to reverse engineer those things. I think if we want to study that relationship on a deeper level, we now have a unique opportunity in information systems, these huge computer systems, because they're becoming so complex and because we have full access to all the layers from top to bottom. We could, if we wanted to, engineer systems to put that traceability, to put that causal traceability into systems, excuse me, in order to answer some of those questions of what happens when we cross certain barriers of complexity and information, and how things interact across scales. I do believe that's an exciting challenge, and maybe somebody, if it becomes economically viable, will be able to do that. But probably the forces are against us because the economics of engineering tend to work in the opposite direction, encouraging us to hide that information and reduce the cost by eliminating information from all levels.
Yeah, I feel that's the problem with quantum mechanics. It's so promising, but there seem to be like 5 people on the planet who actually understand it, or maybe 500, but it's a small community, right? And then they have trouble explaining it to anyone else because obviously there's so much still going on. That's my personal gut feeling. You might not share that at all. And I felt, what if we have this discovery and it seems so amazing, shouldn't we come up with a machine that reduces complexity so much? But we haven't had that. We haven't seen it yet, at least from my knowledge. Maybe it is in a lot of machines and we just don't know about it.
I think some things are just complex, and trying to reduce it will reduce our understanding of it as well.
Yeah.
Feynman was famous for saying that probably nobody understands quantum mechanics. He may be right, but my understanding of understanding itself is that what we mean by understanding is that we can tell a good story about something, right? You tell me, you ask me a question about something I believe I know something about. I tell you the answer. You say, but why the answer? And I explain the answer in terms of something else. And you say, but why that other thing? And at
But
point,
predictive models, right? So if you don't know the why, the predictive models might be okay too.
Yes, but the point is this. At some point, we stop because we just run out of energy. There's always another why you could ask. It goes on infinitely.
Sure.
You can never get to the bottom of everything. But at some point, we simply say, oh, you know what? I trust the rest of it. It's down to trust. And when I believe, I trust this bit, I don't need to question it anymore. And then I understand it. Or then I believe that I understand it. It's an emotional response to resolve never-ending regression in prediction. And that is the function of, I believe that's the function of emotion in reasoning as well. Reasoning cannot work without emotion because it's that emotional resolution that terminates the infinity of connections, of causal connections that explain things. And so
that's so interesting. I never thought about that. That's so interesting. That's fascinating.
I believe that's when we will come to feel good about the world. We'll eventually feel like, okay, you know what, doesn't matter. The rest of it doesn't matter. But everybody has their own point. So some people will say they understand quantum mechanics because they can solve Schrödinger's equation. Some people will say that you need to know the measurement problem. And they go to Bell's inequalities and they say, now I understand quantum mechanics because I can write down these expressions, or I know coherent states, or there's always another level. But until people make their peace with the story and where they're willing to stop, then they never understand anything, right? We never understand anything. So it's really a choice. Understanding is a choice.
I have to think about that. That's fascinating. I never thought about that. You're absolutely right. I mean, yeah, it's a way to avoid this indefinite work that we would otherwise have. And we always have to live with this limited amounts of parameters that we can solve for, limited amounts of variables we can solve for. And I can't even build a fridge, which doesn't seem to be so complicated. But I couldn't do it. If all the fridge manufacturers got out of business, I couldn't do it on my own. It's just, maybe the internet, some YouTube video will help me. But there's so many steps in between that I would have to solve. It seems incredible, but yet I say I understand a refrigerator completely, which is bogus, right? I don't understand any of it. Mark, thanks for doing this. That was really fascinating. I learned so much. Thanks for taking the time. Incredible insight.
Thank you for inviting me. It's been a pleasure.